David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, remember that you can adjust the playback speed as you desire. Second, you can pause the video at any point to jot down notes or write down questions. Third, you can turn on the captions so you can read my words on the screen. Today's lesson covers population growth. And this lesson is in a chapter on sequences and series. So guess what? This means that we can treat population growth like a sequence. So check this out. Population growth can be treated as a sequence. And I've got a little hypothetical example here to show you that. This could be like bacteria cells in a test tube. And so at the start, at 0 hour, we have 1 cell. And then every hour we just double. So every hour, every cell that's in there splits into 2. So after 1 hour, we've got 2 cells. After 2 hours, we have 4 cells. After 3 hours, we have 8, 4, 16, all the way down to 11 hours. Now we have 2,048 cells. So this is just a basic doubling function. All right, now I want you to answer a question. Taking a look at that population growth sequence, is it arithmetic or geometric? Pause the video, look at the numbers real hard, come back. Okay, let's see how you did. It's definitely geometric. Now, just for bonus points, I want you to pause the video and write the formula for that sequence. All right, let's see how you did. So this is a little bit of a tricky one. You have to do 2 times 2 to the n minus 1. And then look how it handles 0. When I put 0, you term U0, that's for the 0 hour, when we start our experiment with just 1 cell in the test tube. We're going to do 2 times 2 to the 0 minus 1. That's 2 to the minus 1 power, which is the same as 1 over 2 to the 1 power. So we have 2 times 1/2 equals 1. So that's how we work that little trick with a U0 term as our start. And then as you calculate, you can see that as I plug in my increasing n, I'm going to get my right values for my population. So population growth can be modeled as a geometric sequence. Let's do an IB type population problem that is broken up into a lot of parts. So check this one out. In 2015, a city's population is 13.491 million people. Big city. In 2016, 405,000 people move into the city and 331,000 move out of the city. So this problem is heavily scaffolded. So part A, find the net change from 2015 to 2016. Pause the video and do that. I'm hoping you got that one no problem. The net change is just how many moved out subtracted from how many people moved in. So I did that there. So I got a net change of 74,000. It's a positive number because the city's population increased by that amount. So there's our net change from 2015 to 2016. Now we're being prompted to find the growth rate. So think about how you calculate a rate based on what you have here and what your population is. All right, let's see how you did. The rate of change is just the amount of change divided by the total. In this case, here's the net addition of people, and there's the people we had before we added that many. So we just divide it through. Now, you can't divide 74,000 by 3.1491 million unless you convert that into its full number. So I did that there. I divided through. I get 0.00549. Now, if I'm going to report that as a percent, I've got to move my decimal 2 places, and I get 0.549%. All right, let's do part C. We found a rate of growth based on those numbers, the net increase over 1 year's period of time. So now what we're going to do is we're going to assume that that rate stays the same over multiple years, and we're going to be prompted here to write a formula that would let you calculate the population based on any year in the future, next year, 10 years from now, etc. So pause the video, think real hard about that, and you might need to remember some tips and tricks that we did when we did compound interest in our last lesson. Let's take a look. So UN, this is our sequence notation, is U1, which is the amount that we have in our first year, times 1 plus the rate as a decimal. So that was 0.00549 to the n minus 1. Now, one way to check to make sure we have this right is when we're looking at the first term, u1, n is 1, so 1 minus 1 is 0, which means this goes to 1. Whatever to the 0 power is 1. So we're going to get this number for our first year, which is correct. That's our starting number. Okay, so there's your formula. All right, now let's do a calculation. Let's figure something out. Find the city's population in 2025. So pause the video, use everything we've done so far, put in your calc, and figure that one out. All right, so here's how we did that. I just did my plug-in step with my U1, my 13,491,000. I did my nice rate here, raised to the 10th power. Now realize, it's the 11th term we want because 2015 is the first term. So if you count as 2015 being 1, you need to go all the way to 11 to get to 2025. So that's a little slippery there. You want to make sure you do that right. So when I do the math on that, I get 14,250,224.28. Now, I want you to take a look at that number because we need to do some things to it just to make it reasonable for our problem. So there's two things we need to do. Pause the video and think real hard and see if you can come up with two things. Okay, thing one. I'd like to meet 0.28 of a person. 28/100ths of a person does not exist. So we can't do that. So we didn't get all the way up to 225, so we can cross that off. However, there's one more thing we need to do. And it relates to the numbers that are here in the problem. So check this out. Every number here has thousands with no people. 405,000, 331,000. Now you know in reality that there were some numbers there. It's not going to be perfectly to the nearest 1,000. Same thing with this one. It's not going to be perfectly to the nearest 1,000. There's going to be some people in that number space. So our answer shouldn't have this kind of precision in there because it's not possible from the numbers that we started with. It comes because our rate of growth has a lot of decimals to it. But actually, in terms of our calculation, we should really just write 14,250,000 like that and carry the same precision that we had with our starting numbers into our answer. So this is a better answer for this problem. Let's do one more example, this time with a bacteria culture. So similar to that one we opened this lesson with. So what we have is time in hours, so elapsed time. So at the 0 hour, our starting point, we have 125 little bacteria swimming around in our petri dish. After 6 hours, we have 350 bacteria. After 12 hours, 980. After 18 hours, 2744, and so on. So your first prompt, create a formula for the growth of the bacteria. We want to create a formula that will allow us to predict what it's like, say, at 24 hours, or what it's like at 36 hours, and so on. Let's see how you did. So here's my formula. UN, that means the population after how many chunks of time, is 125, that's our starting number, times 2.8 to the n minus 1. And I want to call your attention to something here. I defined each n as 6 hours. That's how they give it to us, so I'm going to use that and keep my formula simple. Now, you might be asking a question. How did I get 2.8? So there's a really easy trick to find r for a geometric sequence if you have two adjacent terms. So check this out. R is always going to be un divided by un minus 1. So what I did, I just took this is u1, no, u2 divided by u1. 350 divided by 125 gives me my 2.8. So if you know two adjacent terms, you can always find r. Okay, so here's that question. I brought the formula back over from our last board, so we have that for reference. How many bacteria at the end of the second day? Okay, so first assumption, this is the start of the first day. So go ahead, pause the video, figure out what your n is, and do your calculation. So let's break this down. If n, here n is 4, we are at 18 hours. So 5 would be at 24, 6 would be at 30, counting on all the way up to 9, n for 9 gives us 48 hours. That's the end of the second day. So that's our n for our calculation. So now, pause the video, use the formula, and do that calculation. All right, plugging in. My n is 9, so I raise to the 8th power. That's raising 2.8 to the eighth power times 125. And check this out. That's 472,452 bacteria. Talk about growth. We started with 125. 48 hours later, we have about 500,000 bacteria in there. So these things grow quickly. All right, one last problem here. When will the bacteria population exceed 250,000? Okay, so think about that. Think about what you're solving for and write an equation for that and see if you can take it all the way through to the end and find out when that will happen. All right, let's see how you did. What I get here is 250,000 has to be less than this number where I have my n. I don't know the number of term that would take me to get to the point where the population is greater than 250,000. So now I'm just going to treat this like an equation going forward. I want to find the n that hits that number, and then I just have to say it's past that point in time. So what I have, I divided through by 125, and I get 2,000 is less than 2.8 to the n power. Now I'm going to use logs to solve this. You could also use a graphing calculator, but I think logs are pretty straightforward. So I have a number raised to an unknown power equals another number. That's the same as saying log base 2.8 of 2,000 equals that power. And when I put that in my calculator, I get 7.38. So what do you think about that? We're not done. So think real hard about our problem, some assumptions that we made in the beginning, and then you can be done. Okay, so here's the thing, is we found n, right? But each n is 6 hours. So we need to multiply that by 6 to get our hours. So just past 44.28 hours, our population will exceed 250,000 bacteria. Now, 44.28 hours is the same as 1.85 days. Now, I want to give you one more thing to think about. We could have set this problem up with this table and asked you this question first. So this problem got scaffolded pretty well because it first prompted you to write the equation, then it had you do a straightforward calculation, then it had you do this more complicated one where we solve for an n. But the IB likes to mix things up a little bit, and they can add a lot of critical thinking to what is possibly a more straightforward problem by just going to the C part here and asking you to do that. And you have to realize, oh, first I need an equation. Oh, second I should test my equation, make sure that works right. And then 3, now how do I use the equation to do this type of problem? So if I started with this, it would make it a much harder problem. Same scenario. Now that you've watched the video, take a moment to jot down additional notes, some questions for class, or a short summary of the lesson. You can also go back and re-watch the portions of the video that were a little bit challenging for you. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.